Live. Okay. Okay, so let's start today's lecture, right? So we are going to start from where we left off yesterday regarding prefetching, right? And then we are going to kind of brush up what we learned yesterday and then take it from there. So the goal of today's discussion is to see more advanced prefetching techniques, right? Pattern mining algorithms, and hopefully I would try to convince you that there are lots of opportunities here in regarding, let's say, data driven architectures, right? And how we can design such systems, right? Okay, so yeah, so yesterday we looked at these four questions, right? What, when, where, and how for prefetching, right? So what addresses do we need to prefetch? When do we need to initiate a prefetch request? Where do we want to fetch the prefetch data? Where do we want to place the prefetcher? As well as how do we want to issue a prefetch request, right? I mean, how exactly prefetcher is operated, who operates it, and so on and so forth. So yeah, so we had like this sort of, let's say, outline that we have covered yesterday. So for today's like discussion, we are going to specifically focus on these two points, right? That hardware prefetching algorithms, as I said, like we are going to cover some more, let's say, sophisticated prefetching algorithms, right? And then we are also going to look into something what we call execution-based prefetching techniques, and it would be let's say clear in some time. So before we move further, do we have any question from yesterday's lecture? If we have some. Okay, yeah. Good. But can you press this one? I'm sorry. Okay. So your question is that what happens if a software prefetch instruction prefetches the same address back to back, right? Yeah. So prefetch instructions are essentially, it's a so what happens if you have a two back-to-back prefetch request? If the so let's consider two scenarios, right? So both these instructions have executed so far apart that the first instruction has already completed fetch the data to the cache hierarchy. Now the second instruction is executing. So the entirety of the goal of this second instruction would be to fetch the data. So the data fetching would work like that. Okay, I'm going to first look up the cache hierarchy, whether the data is already there or not. It would see that the data is already there, so it would just simply complete there. It won't do anything. If now let's consider the second option, that these two prefetch instructions are happening so back to back that the first one has not completed yet. Completed in the sense the data has not even fetched back to the cache hierarchy, right? But then the second one has already started prefetching the same thing. So we have something called status handling register in the cache hierarchies, right? So at every cache level, you are going to look up the cache hierarchy, and then if that request is missing, you put it in the status handling register and then send the request to the lower levels of cache. Let's say if you are in at L2, then you would send the request to LLC, that would go to main memory, come back, and so on and so forth. So at that case, if the second instruction comes in and it tries to prefetch the same thing, it would say that, oh, somebody already is trying to prefetch the same guy, right? So that same address is already missed this cache level and then went outside. So it would just simply attach to that same status handling register. It would say that, okay, I'm not going to issue a new request again. When that request comes in, it's going to do the job for both of us. Does it make sense? Yeah. Any other questions? Okay, so if not, then this is the agenda for today's meeting, right? So first we are going to kind of, let's say, bridge from yesterday's discussion, right? That we got a question from YouTube that, oh, what happens if you design a memory controller in presence of prefetcher, right? So does the prefetcher does the memory controller take the prefetcher into account, or is it some completely, let's say, oblivious to prefetching techniques, right? So that's what we're going to cover here, like prefetch-aware system design, especially on the memory controller design. And then we're going to go for advanced prefetching techniques like RL-based prefetching. And then we're going to briefly touch upon something which is, let's say, not exactly prefetching, but it's also a technique to hide the memory access latency. So that's what we call off-chip prediction. And then we will end up the lecture discussing execution-based prefetching techniques. Okay. So let's first discuss the prefetch-aware memory controllers. So prefetch-aware memory controllers is, so this is the work that we are going to discuss here. So as you can see, so Professor Mutlu's student has done this work while he was a part of UT Austin research group, right? So before moving into this work, let's I guess you have already know this, but I'm just going to reiterate. So so DRAMs are typically organized like this, right? So you have some rows and then columns of DRAM cells essentially, right? So, and each DRAM bank has something called a row buffer. So row buffer, you can think of this, let's say when we are reading a DRAM bank, we actually not only like we don't read a cell, we read the entirety of the row, right? So we read it and we put it into the row buffer. Now, when we are going to request a data, it's first going to check the row buffer. If the data is already present in the row buffer, it's called row buffer hit. It's going to return the data much faster than if the data is not in the row buffer. So let's say the row that you are going to request is not the row that is open. So this is what we call an open row, right? Then what you do is you have to store back this row into the DRAM bank and open the row that you are demanding now. So that actually adds the latency. So the crux of this organization is that it creates a non-uniform access latency. So if you have a row buffer hit, then the data service latency is less as compared to if you have a row conflict. So as a row conflict means the data that you are going to access is not the row that is open. So you have to close the open row and then you have to open the new row. That's the row buffer miss basically. So as I said, like the row buffer hit latency is it's lesser than the row buffer row conflict latency or row buffer miss latency, and this essentially creates some sort of let's say opens up a possibility to schedule instructions in a way that you're going to exploit, let's say, as much row buffer hits as possible, because that they are going to be serviced in much faster latency as compared to the row buffer misses. Right. So yeah, so we have prior works like prioritize row hit accesses to increase DRAM throughput that essentially, as I said, like tries to improve the row buffer hits as much as possible so that we can, service the data as lowest latency as possible, right? But then if you have, let's say, now a system that has prefetchers implemented, right? Then how to, prioritize this request, like how to prioritize the prefetch request as compared to the demand request. So we can come up with, two basic policy. It's like simplistic version, right? So one policy says that, okay, I'm going to always prioritize demand first, right? So that's what we call a demand first policy. It always prioritizes the demands over the prefetch request. Makes sense, right? Because demands are coming from the core, so that might be more useful as compared to the prefetch request, which is, the hardware or the software itself is generating. But then there are, you can think of another prefetching, like another prioritization policy, which says demand and prefetch equal. So I'm going to, treat both of these requests as equally critical as in every aspect, right? So they're getting treated the same. But then the thing is, like, if you do the evaluation, which I'm going to show next, right? Neither of these policies essentially perform the best in every aspect, right? So because they do not take account both these considerations, non-uniform access latency of the DRAM systems, right? That row buffer hit latency is lower than the row buffer miss latency. And they also do not consider the usefulness of prefetch request. Like, for example, you're not saying that, okay, I'm going to wait for my prefetch to be more accurate, and then only I'm going to, have this equal policy. If my prefetch is inaccurate, then probably it's better to go for demand first policy. So there is no dynamism in these cases, right? So we are going to add that dynamism here. So the key idea or the key mechanism of this work is what they call prefetch-aware DRAM controllers, right? And so it's composed of two techniques: adaptive prefetch scheduling, as the name suggests, like we are going to schedule the memory request based on some priority. So priority in the sense, the whole goal is to increase the DRAM throughput by exploiting the row buffer locality when the prefetches are useful. That's the key part, when the prefetches are useful. So you're going to add some dynamism, and that dynamic behavior is going to kick in based on some system level feedback. Let's say, for example, how accurate my prefetcher is. And then we are going to also delay the services of prefetches whenever they are useless. Okay, so that's the first technique, the prefetch adaptive prefetch scheduling. And the second technique is the adaptive prefetch dropping. As the name suggests, it basically says that, okay, if my prefetch request, I have an intuition that it's going to be useless, then I'm just going to drop those requests, right? So it's like, okay, I'm not going to entertain something that I know that it's probably going to be useless. Uh, so the overall goal here is to improve the performance and bandwidth efficiency for both the single core system as well as a chip multiprocessor systems, like multi-core systems that we all use in processors in today, right? And then also have a low cost and easily implementable solution for this matter. Okay, so now let's dive into how we like evaluate this thing, right? So how we implement this thing. So recall that prefetch accuracy is just a like a ratio of prefetch used divided by the prefetches sent, right? So we can compute this prefetch accuracy using very small let's say counters, right, inside the hardware. Like for example, prefetch bit per L2 cache line, MSHR entry that I just discussed, like MSHR entry in instance, it's misstatus handling registers. If you are not familiar with it, I would say look into the DDCA lectures. There we discuss misstatus handling registers in much more detail, right? And then you can also have a small prefetch send counter, prefetch used counter, and then prefetch accuracy register. Essentially, prefetch accuracy register is just a division of prefetch send counted by the used counter, right? So whenever your prefetcher is making a decision, you're going to update the used counter. Whenever you are going to have this prefetch bit, let's say set, then you are going to update this update the used counter and so on and so forth. So essentially you are going to measure this we are going to measure this counter values dynamically at the runtime, right, inside the hardware, and we are going to make the decisions accordingly to the prefetch accuracy. Okay, so now let's see. So this is how the overall the APD adaptive prefetch design, DRAM-aware prefetch controller looks like. So we have two components, the APS components and the APD component, right? So let's start looking at the adaptive prefetch scheduling component first. So scheduling component essentially says that, okay, I'm going to set a priority for the scheduling, right? So how exactly the priority is scheduled? So let me define this scheduling levels, right? So we're going to set the priority of the prefetch request. Either we can say that, okay, if my prefetch accuracy is low, right, then I'm going to prioritize the demands from the core, which makes sense because prefetch accuracy low means both the things are happening. So your prefetch requests are not that useful. That's one thing. And the second thing is like the demand request that is coming from the core, they are much more, let's say, exposed, right? So there is no prefetch that can hide the latency for those demand requests. So it makes sense to prioritize demands from that core in that case. But if the prefetch accuracy is really high, then we are going to treat the demand and the prefetches as equal parity as possible, right? So that's the idea here. So so yeah, I'm going to repeat the same thing again, that in a CMP system, prioritize the demand request from a core that has many useless prefetches, because the code that in which the prefetcher is not working correctly, then the demand requests are completely exposed to the latency of the demand requests are kind of exposed, right? So in that case, we are going to prioritize the demand request from those cores even more. So yeah, so based on this priority ordering, right, we are going to define two types of priority ordering. So one we call critical request, another one we call the urgent request. So the critical requests are essentially the ones that are all the demand requests are by default critical, and then the prefetch requests are also be called critical if it's coming from a core where the prefetch accuracy is significantly high. Okay, so what do we mean by significantly high? It's basically we have some sort of threshold that is statically set at design time, and if the accuracy is higher than that threshold, we are going to say that, okay, my request for those cores are essentially critical. Okay, and then we have the urgent request as a category. So urgent request essentially says that, okay, all the demand requests from the cores where the prefetch accuracy is lower than the promotion threshold, I'm going to call it as urgent request. Okay, so now let's see how the prioritization order looks like. So we have so this is the statically fixed prioritization order. So you are going to prioritize first critical request, then the row hit requests that are going to hit inside the DRAM row buffer, right? So that's also taking into consideration of the row buffer misses and row buffer hits. So that's essentially the part that makes it let's say DRAM row conflict aware, right? And then I'm going to prioritize the urgent request, and in the end, the last prioritization order is the oldest request. So if none of these are essentially present, then I'm going to treat the oldest request from the queue. I'm going to send it to the memory. So that's the prioritization order that this proposal decides. Now you can always come up with this question saying that, okay, what happens? So the thresholds that we see here, right, the promotion thresholds, are they also dynamic? The answer is no. So they are kind of, let's say, statically fixed. We have the way to fix these thresholds are like, okay, I have seen lots of we have evaluated lots of workloads, right? This threshold is working, let's say, pretty decent in all the workloads. But then you can always say that, okay, having this sort of, let's say, statically fixed let's say threshold, and then doing the prioritization based on that statically fixed threshold might not work for all the workloads. It might not work for all the situations also. Let's say, what's the guarantee that that same threshold is going to work well if you have, let's say, even a faster DRAM? So that you can question those things. And you can also question, let's say, is this the best that we can do in the prioritization order? What if we can make it even more fine-grained? So all I'm alluding to is basically that these, let's say, heuristic-based design, right? You have a threshold as a heuristic. You have a statically fixed prioritization order, right? So this heuristic-based design, it works. It definitely works well than the designs that are completely agnostic of these behaviors, right? But then they are not necessarily the best that we can come up with. So if you can come up with a solution that is, let's say, much more dynamic than these ones, let's say I'm going to set the thresholds, change the thresholds dynamically, right? Then those policies they have the possibility to even outperform these statically designed, let's say, prioritization policies. So that's my 2 cents essentially. So now let's go to the second component of this memory controller, which is the APD part, the adaptive prefetch dropping. And this part of the component is like relatively simple, right? So it essentially says that I'm going to proactively drop old prefetch requests based on the accuracy estimation. So so old requests are likely useless because of these 2 reasons, right? The APS, the promotion policy, already prioritizes the demand request when the prefetch accuracy is low, right? And then if a prefetch that is hit by a demand is already promoted to a demand also. So in that cases, the old requests are likely going to be useless. So in that case, what we are going to do is we are going to say that, okay, why don't we just simply drop those requests, right? Because they are prefetch requests, so they are not necessarily, let's say, processor is not actually stalling on those requests, right? So prefetch request, as I said yesterday also, is like a best effort hardware system, right? So I'm going to prefetch it, but then the core is not essentially stop its execution based on whether the prefetch data has come or not. So in this case, if we just simply drop that request, that's also going to be, it's not harmful from the program's progress. It's not harmful for the program's correctness also. Okay. So that's what we are going to do here, that if it's an old request, that we are just simply going to drop the old request. That's going to save the resources, scarce resources like, memory bandwidth, cache pollution that we have discussed yesterday. And, if we mitigate these pollutions, if we mitigate this bandwidth usage, then that's going to bring us performance benefits. So that's what I'm going to show here. So I'm not going to go too much detail into this thing. So let's see the the performance here, right? So you're seeing like 3 bars here, right? The 3 clusters for the single core system, for the 4 core system, and for the 8 core system. So what we're showing here, that if you have, let's say, 2 static policies, right? The demand first policies and demand prefetch equal policies that we just discussed. And then we have this dynamic, adaptive policy, which is the prefetch aware DRAM controller, right? So in single core, 4 core, and 8 core, all the configurations, the adaptive policies essentially outperforms both the static design policies, and it also outperforms the no prefetching policy. And the second thing that you should also take into account is that the more we go into this like constrained environments, right? Let's say 4-core system, 8-core system. Today's processors are like even more crazy, right? So like for example, AMD has 64-core system, right? 128-core system they are coming up with. So there you're increasing the number of cores, but not all the resources are actually scaled in the same way, right? So you don't have, let's say, the necessary so from 1 core to or let's say from 4 cores design to 128-core design, your main memory bandwidth not necessarily increases by the same scale as the core is increasing. So what happens is your per core main memory bandwidth is actually getting lower and lower, right? Similarly, your shared resources, like for example, last level cache, the size of the last level cache also might not increase in the same scale, right? So in those cases, if you actually reduce and have some sort of dynamic policies like prefetch-aware DRAM controllers, right, that can provide much more performance benefit in these constrained environment as compared to a single core environment. Like see, the gap is essentially lower. Okay, so that essentially says that I mean, if you are more interested more, definitely check out this paper. So it's so the crux of this problem is essentially that if you make your let's say DRAM controller prefetch aware, right, that actually brings up performance, right? That and especially provides performance benefit in constrained environment like multi-core systems or maybe server processors, which is heavily constrained in memory bandwidth and so on and so forth. Okay, but then you can also think of, let's say, other policies that can be made prefetch aware. Like for example, let's say the replacement policy, that is the cache management policy that is happening inside the last level cache, right, which is shared across all the cores. Maybe we can make that also let's say prefetch aware, right? So it's going to, it's in the same way, right? It's going to consider when the cache block is getting filled into the cache, it's going to take into consideration whether it's actually fetched by a prefetcher or whether it's fetched by a demand request by the core, right? And then it can adaptively change the policy, saying that okay, if my prefetch request is useful, let's say I have a notion of accuracy and I have seen that my prefetcher is historically accurate, then I'm going to say that okay, I'm going to put this cache line into much higher priority in the cache so that it stays in the cache for a longer time, as compared to if my prefetcher is inaccurate historically, then I'm going to say that okay, I'm going to fetch it inside the cache, put it inside the cache, but let's put it in the lower priority so that if you have to kick out something, you would that would be the usual suspect, you are going to kick out a prefetch line itself. So that's the idea there also. So you can also take a look at prefetch aware cache replacement policies. If you are interested, definitely reach out to us and we can give you more pointers over here also. Okay, so do we have any question in prefetch aware DRAM controller till now? Okay, so if not, then let's go to the next let's say topic, which is the self-optimizing prefetcher. So that's, now we are going back to the same let's say the discussions that we have left yesterday, and seeing the progression of the complex prefetcher, right? And we are going to catch up from there. We are going to see even more let's say sophisticated version of prefetching algorithm. So we actually authored this paper a couple of years back. Wow, time flies, huh? So we authored this paper a couple of years back that was presented in Micro 2021, right? So the name of the paper is Pythia, a customizable hardware prefetching framework using online reinforcement learning. So let's dive deep into the topic. So before I go into this, has anyone used reinforcement learning in any other work? Let's say deep version of the reinforcement learning or some machine learning coursework. Have you ever used it? No one? Okay. Sorry? Okay. You have heard of it, never used it. Okay. So let's go and take a look at the basic principles of reinforcement learning then, and then maybe we can say like we can formulate the problem of reinforcement prefetching as a reinforcement learning problem. Okay. So you have probably heard of reinforcement learning in so there is this work from Google DeepMind. At that time, it didn't used to be called Google DeepMind. It used to be called only DeepMind, right? So they used reinforcement learning, a deep version of reinforcement learning, like deep RL networks, right, to outperform the the best champion, the Go champion, Lee Sedol, and I think this was in 2018, I guess. So they came up with that AlphaGo, right? That's what they call. And AlphaGo outperformed the reigning champion at that time. And since then they have actually made a lot more progress on this thing. And like couple of years back, or like, I think last year, they have also demonstrated like a multi-agent reinforcement learning. Like all the agents, like there would be multiple systems in that agent, and they're kind of communicating with each other to share the common goal. The common goal is to win Dota. And they have also demonstrated that they have outperformed human champion Dota players by like a reinforcement learning based solution. So if you're interested, definitely check out those videos, check out those papers, and it's like really interesting. So we are going to see the similar kind of approach here, but unfortunately, what we are going to, let's say the trade-offs for us is not exactly the same trade-off for, let's say, the Google folks. Okay, like for example, for them, they can actually throw an entirety of the GPU system, all the GPUs in the world, to come up with the best Go move, given your opponent has already made a move, right? So you can look way into the future, and that's how these models actually outperform the best human experts also, right? But what we are going to see is like we are going to implement this inside the hardware, right? So your this prefetching framework, right, which is done using reinforcement learning, it's actually implemented inside processors. So we don't have the same amount of, let's say leeway, right? So same breathing space as they have, right? So now how we can still design a system as like which is still hardware realizable in the end, right? We can make it work inside the processor at the same processor frequency, right, in the scale of nanosecond, as compared to, let's say, in the scale of seconds or even minutes in playing chess or playing Go, right? So that's what we are going to discuss in this work, and hopefully I can motivate, let's say, future works on this direction also. Okay, so let's see. Before going too deep, I'm just going to discuss a bit more about the basics of reinforcement learning. So reinforcement learning is an algorithmic approach to take an action in a given situation to maximize a numerical reward. So take a note of these three keywords, right? Action in a given situation to maximize a numerical reward. So every reinforcement learning setup is essentially comprised of at least two key systems, right? So there is an agent, and the agent resides in an environment. Like you can think of environment as, let's say, the Go board, right? The state of the board. That's not the state of the board, the board itself, right? Perceiving that board is the perceiving the environment, right? You can think of, let's say, the Dota state as the environment, right? The agent resides in that Dota game, and then it has to decide, it has to sense the environment, where is your enemy, where is your obstacle, and so on and so forth. And it, based on that sensing, it needs to take an action, and that action taking, for each action, it's going to get a reward, right? So reward can be, let's say, as good as, oh, I have killed an enemy, right? Or maybe I have found a new let's say, treasure, right? So that like positive rewards, negative rewards, and so on and so forth. So agent senses the environment, as I said, in what we call a state at every time step, right? So that's ST. And for every state, it basically takes an action, right? So action that, it does in that environment. For every action, it takes a reward, gets a reward from the environment. As I gave an example, like reward can be positive, reward can be negative, reward can be as, as simple as, let's say, you won the game in the end, right? Or reward can be as fine-grained, let's say, I found let's say, treasure. I found some shortcut, right? So that's your reward. So essentially, what the agent learns is something what we call Q values for every state action pair. So Q value, you can think of this as a expected return that the agent has a perception that, oh, if I'm going to take that action in that given state, I'm going to get that reward. So that's the expected reward for that state action pair is represented by that Q value. So what the agent is doing is essentially learning this Q value and making, and any given state, it actually going to take the action that gives us the highest Q value. So it basically says that, okay, I'm going to go in a greedy policy, right? And I'm going to say that, okay, I'm going to take that action in that given state that's going to give me the highest expected reward. Make sense? Now you can also you can easily, if you're thinking let's say a bit more deeper, you can say that, oh, if I'm always going to exploit the action that's going to give me, let's say, the highest reward that I know till now, then how exactly I'm going to make sure that, okay, I'm going to explore all the possible actions, right? You can actually end up saying that, okay, once my agent starts learning, right, it might actually go in a perpetual loop saying that, okay, I have explored two actions and I'm always going to exploit those two actions, saying that, okay, that's the best thing that can happen. So it might not actually ever explore all the possibilities, right? So that's why we have also something called, in the paper we have explained a bit more clearly, right? We have something, and if you're interested, definitely check out the theoretical side of this story. So we have something called epsilon greedy algorithms, right? So epsilon greedy algorithm says that, okay, most of the cases we are going to explore the action that gives us the highest Q value. But in some cases, we are going to take a random action, right? That might not give us the highest Q value, but that randomness enables us to explore the state action space. It just says that, okay, what if in that state, if I'm going to, go to the left, right? I mean, maybe you have died, right? The game restarts. But in nonetheless, you're getting that negative reward. In the same way, you might also end up seeing a positive reward in some cases, and that makes the agent explore that state action space. Okay, is this clear? Kind of. Okay, so now let's see how we can formulate that prefetching. We can say that, okay, prefetching is completely different than this. Right? I mean, how exactly you can even think of prefetching as a reinforcement learning problem? It appears to be that it's not that different if you think in this way, right? So our prefetcher acts as a reinforcement learning agent, and the processor and the memory subsystem acts as the environment for the prefetcher, right? So it is literally where the prefetcher sits in, right? So now at every time step in this case is whenever it sees a demand request. Yeah. So whenever it sees a demand request, it senses the state of the system. It says that, okay, give me some feature values, right? Feature values in the sense like, okay, who generated this memory request? What is the program counter value of this memory request? What is the last few addresses of that that has been generated by the same instruction? What is the delta between those addresses? All of this information that you can think of can be used as a feature to sense the state of this environment. Okay. And now once you sense the state, you can take a prefetch action. So prefetch action in this case would be as simple as that. Oh, if I am accessing this prefetch, if I am demanding this cache line A, I'm going to issue a prefetch request O offset ahead of A. Let's say A plus O, right? You can always think of this O as negative value. So that means you can go negative side, but that's essentially a prefetch action, right? So given this state, I'm going to take an action that, okay, how far ahead of the current demand request I'm going to issue a prefetch request. So that's the formulation. And for that prefetch action, you are going to get a reward. I'm going to show you how the reward is defined, right? And the reward essentially, is what makes this prefetcher learn the correlation between the state and the action. Okay. So now let's try to take a closer look at each of three of these pillars, right? The state and the action and the reward more clearly. So what do we mean by state? So state is essentially a k-dimensional vector of features, right? So features are further composed of control flow information and the data flow information. So control flow information you can think of as let's say program counter value, or let's say what are the branches that you have executed beforehand. Okay, so what are the last three programs, like basically the path of the execution that you're seeing, right? Or let's say the last three branch pieces, right? Or I have seen that branch, and then I have taken that if case, I have taken that else, I have taken that if again. So that gives you a path of the program where it's actually executing. So that's what we are calling the control flow information. And then we can have data flow information. Data flow information is essentially coming from any information that is from the data side, right? So what is the current cache line address? What is the last cache line address? What is the last 4 cache line address? What is the delta between last 4 cache line address? Like literally anything that you can think of in this direction can be used as a information that we can use to start learning using as a state information. Okay. So now let's see what is the action here. So action, as I said, that it's just as simple as going to find that offset, right? That I'm going to issue this offset ahead of me. Now, offset can be legitimately negative. And now, if you think of, let's say, a traditionally sized machine, right, which has, 4 KB physical page and 64 byte cache line. So why we are caring about the page here? Because typically when we issue like if we design a prefetcher in the physical address space, we normally do not cross the physical page boundary. Okay, so that's why we are saying that, okay, inside a physical page of size 4 KB, how many cache lines you can fit? It's the 4 KB divided by 64 byte, which is 64 itself. So if you're any cache line in this page, and if you have a limitation that, okay, you can only prefetch some cache lines within that page. So essentially from any cache line that is demanded, you have the possibility of going either on the -363 to +63 direction, right? So either you can go something ahead of it, or you can go something beyond, behind of it, right? So that's +63 to -63. That's the range, right? So essentially we are looking at 127 actions in this case. Okay, but then also consider this, that a zero offset is essentially a valid action in this case. Zero offset means that Pythia is essentially deciding that, you know what, I don't want to prefetch anything. And we're going to show, like, it literally decides, it has the dynamic capacity to sense when it doesn't want to prefetch based on, let's say, certain conditions, like, oh, my cache pollution is too high, my memory bandwidth usage is too high. You know what? Maybe it's better to stay put. Don't prefetch anything at that case. So that's going to be useful. The zero offset is going to be useful in those cases. But then we can also prune this action space, saying that, okay, not all the offsets are essentially equally likely to appear, right? So then we can exploit that observation, saying that, okay, instead of having this 127 actions, let's have like a very smaller set of actions. In the end, we have actually evaluated using only 16 actions, and we show that 16 actions nearly works as good as, let's say, the entirety of the 127 actions also. Okay, so pruning, why do we need pruning? Because the entire in the end you have to design it inside the processor. So if it saves complexity, both in terms of storage complexity as well as design complexity, right, that helps. Every bit helps. So that's why we can also prune. Okay, so now let's see the rewards, and that's the most quintessential part of making any RL framework work essentially. So your RL framework would learn only as good as the reward that you are going to provide it with. So the reward in this case defines the objective of Pythia. So what is going to be my prefetch objective? What is the golden standard that I'm chasing, right? So that's what is defined by the reward. Okay, so now reward encapsulates two key metrics. It encapsulates the prefetch usefulness, as we have seen before in the prefetch-aware DRAM controller, right? That prefetch usefulness is also considered there in terms of accuracy, that how accurate that prefetch is historically. So in this case, we are going to use the prefetch usefulness, and usefulness can be defined in many ways, right? So how accurate it is, how late it is, like whether it was timely enough. If you recall yesterday's lecture, whether it was timely enough or it was late, in a sense that the prefetch request has not yet been completed, but professor already demands it, right? So in that case, it's late, or maybe it's out of page. As I said, that if you're doing a prefetching in the physical page limit, right? So then out of page is essentially, which we don't normally entertain. There are prefetches that we can design, which goes out of page also, but in this case, we are not going to entertain. So we can consider this out of page prefetches as something, let's say, oh, it's a missed opportunity because you have generated a prefetch candidate that is going beyond the page limit, that is going beyond the limit that you can prefetch. So why don't you, tune yourself? So that's the usefulness here. And then it also encapsulates the system level feedback. So you can think of system level feedback as multiple directions, right? You can think of memory bandwidth usage, it can be cache pollution, it can be energy consumption, anything, right? So you can think of, let's say, oh, if I'm going to devise a prefetcher for, let's say, that is going to work on this M1, let's say, MacBook Air as compared to MacBook Pro, as compared to the full-blown Mac, right? So you can actually design in 3 different energy envelope, right? So MacBook Air might be, much more energy optimized as compared to a MacBook Pro, right? Or as compared to a fully blown Mac. So that's what this system level feedback taking into account comes into the consideration. Okay. And so even though this framework itself can take all any of the system level feedback, but we are normally like we have demonstrated in this paper using memory memory bandwidth as a as an example of the system level feedback. But essentially you can extend this framework for other types of feedbacks also. Okay, so now let me define concretely like what do you mean by rewards. So rewards is essentially defined in 5 levels, right? So accurate and timely, accurate but late, loss of coverage, inaccurate, and no prefetch. So inaccurate and no prefetch, they have like further categorization based on the memory bandwidth usage. So in the end, we are going to get, let's say, 4 here and 3, so 7 reward levels. So each reward level is essentially a value that we set at by some automatic design space exploration and the design time itself. But then setting these values essentially gives the prefetcher, essentially gives Pythia some sort of let's say objective to chase for. And the good part of this design is that you can actually dynamically tune these values runtime in the fly. So the moment you actually change and fiddle around with these values, it also gives a different objective to Pythia, and that makes it interact differently based on this objectives that we are going to define. Okay, so now let's see like what do I mean by the objectives in this case, right? So let me give you some example of let's say the reward configuration and how exactly the reward essentially defines the objective for Pythia. So this is the number scale, right? The number line, and let's say we have defined the reward levels like this. So the 7 reward values we have put it like this. So this is accurate and late, this is accurate and timely. Then if it is no prefetching but then high bandwidth, that's the case. No prefetching in low bandwidth, inaccurate prefetching low bandwidth, and inaccurate prefetching high bandwidth. Okay, so now if I set the values like this, that's just an example, right? You can set it in any way. But if I set it like this, it sends some message to Pythia. What does it send? What the objective it sets? So for the first thing is that we are providing much more, let's say, benefits, right, to Pythia if it comes out to be, if the prefetch request comes out to be accurate, irrespective of whether it's late and timely, but it's definitely higher than all the rewards. Right? So that essentially means that Pythia would be greedy enough to always chase for this sort of actions, right? Oh, if I take some action that gives me this reward, that's going to be the best action for me, right? So we are making it biased, right? So we are giving it some sort of hint that, oh, if I do this, then you are going to get much more reward for yourself. So always crave for generating highly accurate prefetch requests whenever possible. And also, if you see clearly inside this, so we are providing more reward for the accurate and timely as compared to accurate and late. So it's going to prefer generating prefetch requests that is going to be accurate and timely as compared to accurate and late. So that's the first level, indication. Now the second level indication, let's say if Pythia has some sort of intuition that, okay, maybe my prefetch request is not going to be useful, right? In that case, what happens? So if you look into this, if your bandwidth consumption is low, right, then we are providing a slightly higher, preference to the no prefetching case as compared to the inaccurate prefetching case. So in this case, what would happen is that if your memory bandwidth usage is low, then Pythia is going to prefer slightly prefetching nothing as compared to prefetching something inaccurate. You can also switch this thing. You can also say that, okay, if my memory bandwidth usage is low, I'm going to make Pythia much more aggressive. So basically, I would change the values here. I would say inaccurate prefetch would have a higher reward as compared to the no prefetch. In that case, Pythia would become more aggressive if your bandwidth usage is low. But then if your bandwidth usage is high, and it's also not going to make it make a accurate request, then what happens is your no prefetch reward is much higher than the inaccurate prefetch reward. In that case, it essentially gives Pythia objective that, okay, if you are inaccurate, you are likely going to be inaccurate, and your bandwidth usage is high, then you know what? It's probably better to stay quiet as compared to prefetching something rubbish. So that's the motivation here. Okay. So now if I change these reward values, let's say I fiddle around, right? I fiddle around with the reward values and then shift it from here to here, right? So that also sends a different message to people. What does it send? In this case, also we are providing higher rewards for accurate. So it would still chase for accuracy whenever possible. But let's say if it is not accurate, in that case we are providing irrespective of the bandwidth usage, right? Even if it's low or high, it doesn't matter. Irrespective of the bandwidth usage, you're providing no prefetch rewards much higher than the inaccurate prefetch reward. So in this case, what would happen is that if Prithya is not going to be accurate, it simply understands that, okay, it's much better for me to stay quiet as compared to prefetch something inaccurate, irrespective of the memory bandwidth. So this is what we call, let's say, a much more conservative configuration, which is typically useful when you're designing, let's say, highly threaded, highly core server processors, right? And as I mentioned, like they have like less per core main memory bandwidth, or maybe you're designing some processors that is specifically designed for large scale memory bandwidth sensitive workloads, like for example large scale graph analytics applications, right? Yours Meta or Google social graphs, you're traversing the large scale graphs. In those cases it makes sense to have this sort of, let's say, dynamic optimization, saying that, okay, I'm going to design Pythia with a different reward values. Okay. So yeah, so that's what we are going to see here. I'm probably going to skip through this entirety of the design, the flow chart. So you can, if you're interested, definitely check out the paper. So it essentially, we have something called a Q value store, and then you have an evaluation queue. So Q value store is essentially the storage that we have for storing the Q values for every state action pair. And then there is a pipeline flow here, that how we want to look up this Q value store, how exactly we are going to extract the Q values. And then there has been lots of engineering going on even to design this Q value store, because you can think of, let's say, state can be like arbitrarily large. So actions might be limited. You can prune, and an action is kind of, let's say, more concrete. But then state can be like, let's say, anything. Like if you consider, let's say, a state information as, let's say, PC value, right? Program counter value. That can be like, let's say, 64-bit value. So you can literally have like 2 to the power 64 possibilities. Are you going to save for all of them? The answer is no. So you're going to be clever. You need to design it in a clever way, so that we can circumvent those situations, right? So in the paper, we have made a long discussion on how to design it efficiently, to exploit parallelism in the table lookups, and then essentially like a area optimized as well as compute optimized system. Okay, so now let's see some sort of do we have any question till now regarding the design? Okay, yeah. Okay, that's a good question. So the question here is that, okay, do you stop the training at some point? So the answer is that we actually do not have, unlike, let's say, deep learning based supervised learning techniques, right? For example, let's say large language models, or let's say vision models, right? So we don't have a separate training and testing phase. So the beauty of RL framework is that it always learns. So it learns when, let's say, for example, when it's playing against Lee Sedol, right? It's also learning from his actions at that time itself. So that's the same thing that we are also applying here. So it keeps on learning. So this feedback loop, it actually goes on inside the processor itself. So whenever it sees a new demand request, it prefetches something, puts this in the evaluation queue. Evaluation queue gives it some sort of feedback, and it keeps on learning for all the demand requests. So you start with a clean slate, right? And then after some time, your learning gets like good enough. Then you start making good decisions, but you don't stop your learning there. You keep on learning. You keep on learning based on this feedback. And why we can make this sort of approaches here, because we don't, as compared to, let's say, traditional deep learning based let's say models, right? We, in this case, as we have seen shown in the paper, we don't have to do so much of computation. So that's why we can do this thing online. So that's why we have this thing in the name itself, right? That online reinforcement learning. So we keep on training as well as we using the same, model to make the predictions also. Does it answer your question? Okay. But that's a good question. So, I mean, you can also think of, let's say, even more sophisticated prefetchers, right? And then people have explored this thing. They might not be hardware realizable. They might not be implemented in the hardware right now, but then they can actually make use of deep learning-based reinforcement learning, right? So there is something called like deep RL, right? So you can essentially remove these table-based lookups by a neural network, and that makes it much more powerful. But then it also comes with a trade-off of, let's say, much more computation. But then you can handle those training, testing a bit more cleverly, so that in the end you provide even more performance benefit from the same let's say sort of ideas. So yeah. Okay, do we have any other question? You have time? Okay. If not, then let's look into the some evaluation results, right? So so first we are going to see the performance with varying the core count, right? So as we said that when you design a high core count processor, things are actually you need to take much stuffs into account as compared to single core processor design. So here so this is what the prior prefetchers, like they call like SPPEM, law, bingo. There are like lots of prefetchers, right? And if you are interested, then if you go into the prefetching domain, right, you would see like since it has been proposed, let's say 3-4 decades back, right, there has been lots of work going on, and then they are even more, let's say, contextual in today's time, I would argue, as compared to, let's say, what it used to be in an earlier times also. So they're not going anywhere essentially. So you need better prefetching techniques coming up every time. So these are some three prior state of the art works. So that's how they are performing, right? And this is how Pythia performs, right? So as you can see, like it considerably outperforms in every aspects, right? In every core configuration. But then the beauty is that if you look into the single core configuration, and if you see the gap in the multi-core configuration, the gap actually increases, right? So in a single core, we have like 3.4% performance, where in the multi-core, we have like 7.7% performance. So that gives us some sort of intuition that, okay, it's making the dynamism into consideration. And that's why it can provide, higher performance benefit in more constrained environments, right? So that's a takeaway from here. And similarly, we can also take a look at, let's say, different types of system with different, let's say, DRAM bandwidth, right? So this is something called million transfers per second. So on the x-axis, the more you go on this side, it's basically higher the DRAM bandwidth available to you, right? So this is how the previous prefetchers perform, right? And these configurations are essentially practical configurations coming from actual processors, right? As you can see, like you have some AMD configurations, and these configurations are like per core available bandwidth, right? So we are not considering the full let's say full number of cores in EPIC processor, but it's just the per core bandwidth that we have. So in AMD Threadripper, you have per core bandwidth here, EPIC here, Xeon process here, and our baseline configuration is here. So Pythia performs like this. So two things that you can consider here. So first of all, definitely it's across the board, it's improving performance. So that's the good part. But the weird or not so surprising part is that in this kind of, let's say, memory constrained configuration, it's actually better if you don't prefetch anything, because this is geomean speed up over no prefetching, right? And this is the 1 bar. So any number that is lower than 1 essentially means it prefetching hurts performance. So you could have just simply stopped prefetching in those cases, and that's the reason why many server processors, they actually end up disabling the prefetchers when they design those systems for the server class processor. Like you have the same IP, you have the same code design, but when you ship it for a server class processor, you just disable some prefetchers, right, based on some aggression, like statically disabled. But what our thesis here is that you can actually come up with better solutions that takes this thing into dynamism into consideration, and then you end up having, okay, maybe I'm not improving performance, but at least it's not decreasing performance, right? So that's the benefit here. And across the board, if you see the performance gap, right, the gap essentially increases. So that's the key takeaway from here, is that across the board it essentially improves the performance. So if you are interested in this work, you can check out the GitHub repository. We have this implementation entirely online, and you can essentially evaluate the entirety of this thing. Maybe you can check this out for part of your the lab that we are going to release this weekend, right? So it's essentially on the same test bed. So the simulator that you're going to use for this lab, this is implemented on the same simulator, same environment. So you can just simply plug and play this model on your system and then see like how it performs. Okay, so yeah, you can take a look at this. If you're interested, definitely check out other resources, and that's the paper. Yeah, so that's what Pythia is. And again, I'm just going to reinforce this part, that it's an online model, right? So it just keeps on learning online itself. And yeah, so and if you're even more interested in, let's say, reinforcement learning in general, right? So definitely check out this book. So that's let's say the Bible of reinforcement learning, right? So by Sutton and Bartow. So you can see, let's say, more, sophisticated, let's say, recent examples of reinforcement learning, AlphaGo, AlphaGo Zero, and as well as, let's say, more theoretical aspect of reinforcement learning, right? And how exactly you can use reinforcement learning, and they can pop out like in many cases, right? So personalized web services, thermal soaring, human level video gameplay, as I said, like Dota. They have like Google, DeepMind has demonstrated that it can outperform like even expert Dota players also, and that's fascinating in my opinion. So yeah, if you're interested, definitely check out this one. Okay, so I would probably stop here before going into the next part. Maybe let's take a break for. My phone is dead. Oh no, it's still alive. So let's take a break for 9 minutes maybe, and then let's come back at 2:20. Okay, perfect. Okay, let's start again after the break. Okay, so till now we have seen an example of, let's say, reinforcement learning based prefetcher, right? So it's something that works, outperforms the prior best performing prefetchers. And then there is I actually forgot to mention it here, and then I would need to put these slides also. So there is a recent work that came up in this year micro. So that was presented, let's say, a couple of weeks back. So they are advancing on top of Pythia. So Pythia and so that's also a, let's say, reinforcement learning based, but not necessarily the fully the exact model of reinforcement learning that we use. Okay, so there is something called multi-arm bandit. It's a let's say early version of reinforcement learning ways that we all know, live and breathe for today. So they have used that multi-arm bandit, and then they showed that they can actually match Pythia's performance benefit even with drastically low complexity. Right? So, for example, Pythia ultimately needs, let's say, around 25 kb of storage space to store those Q value tables, right? But then their work, it's called micro arm bandit, if I'm not wrong. So if you're interested, I can show you the I can send you the link also. So the micro arm bandit, that paper claims that so they have achieved the similar performance with only fraction of kilobytes of storage. So it's essentially improving on the same direction, but making it much more hardware feasible. So that gives you some sort of idea that this sort of direction is like uh, we need innovation on this direction. Right? So if you want to design some next generation processor, if you want to design a processor that can not only handle, let's say, the workloads that you have tested with, right, but it can equally work for all the workloads that you can throw throw at it in the wild, and all the configurations also, then this sort of let's say self-optimizing self-learning frameworks are pretty useful. Okay, so now for the next work, we are going to let's say divert a bit more from here, a bit sideways. So if you remember, like yesterday when we are talking about prefetching and caching and all these policies to latency hiding techniques, latency tolerant techniques, and so on and so forth. So we have actually discussed that essentially prefetching and caching are latency hiding techniques, right? So they hide latency in a sense that uh, hide latency from the processor's perspective, in a sense that when the processor wants to demand the data, it magically finds it to be in the cache instead of going to all the way up to the slower memory, right? Let's say main memory, off chip main memory, it would find it in the cache. So when processor demands it, it's going to see a less latency. But then the cost of getting the data from where it was residing before, let's say in the off chip main memory, is the same. So we are not fundamentally reducing the latency, but at least as well like as long as the processor's perspective is concerned, we are hiding it. So then the question is that even like Pythia is good, that's fine, and we have seen the performance benefit, but even Pythia, if you look into the coverage, right, the prefetch coverage that we have defined yesterday, that what fraction of the memory request Pythia can actually predict for, you can see only 50% of the memory requests that are going to main memory, they are successfully predicted by Pythia. But then that means that there are 50% still left, like half of them are left, which is still going to main memory, even if you have Pythia inside. So then what's the solution over there? Right? So can you do something better? So we can always say that, I mean, if Pythia is providing, let's say, 50% coverage, if Stride Prefetcher is providing some other coverage and blah, 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 you add all the prefetchers together, right? Make a stack of prefetchers, right? And let's say all of them work at the same time, right? So people use that. Modern processors, many modern processors, they have like multiple prefetchers in the same core, right? So that the idea of that hybrid prefetching system is exactly like that, if I'm going to, if prefetcher 1 is going to cover, let's say 50%, prefetcher 2 is going to cover 30%, not necessarily they together would cover 80%, they would have some, let's say, large bit of overlap, but hopefully together they would come out to be, the coverage would come out to be a bit more than 50%. Let's say each individually they can cover, right? But then in this case, the work that I'm going to discuss next, right? We are going to, let's say, take a step back, and we are going to say that, okay, is this the best thing to do to just stack up the prefetches? Probably not the best. So what else we can do in this case? So we have something called off-chip prediction in this case. So off-chip prediction is essentially, the crux of the problem is that the processor has already requested for that data. Okay, so it has generated the memory address. Now, what happens in the system? The way to access the memory request, let's say if you have a prefetcher, if you don't have a prefetcher, it doesn't matter. So the way to access the cache hierarchies, you would look up L1 cache, then you would look up L2 cache. If it is missing, you would look up L3 cache. All the cache hierarchies all the levels that you have, let's say L4, L5, what, right? So all the levels you would look one by one sequentially. And if everything is, missing, then you would say that, okay, I'm finally going to off chip. I'm finally going to main memory, correct? So each access, if you do it sequentially, that adds latency. So that adds latency in the sense that, okay, I'm going to access L1, it adds 5 cycle latency. I'm going to access L2, it adds 10 cycle latency on top of that. I'm going to access L3 cache, which is typically bigger, right? The bigger means it's slower. So the far away, the bigger the caches that you are going to access, it's basically adds latency. Instead of doing that, if I say that, okay, I know by some magical prediction, right, that this memory request that the processor is demanding is likely going to off chip, then why don't you just cross-cut this entire lookup, go directly to the main memory, start fetching the data. Now, but you're not also killing the actual request that is flowing through the cache hierarchy. Your actual request is anyway looking up the L1 cache, followed by L2 cache, followed by L3 cache, and so on and so forth. But eventually, if you make the prediction correct, eventually it would miss all the cache hierarchy and finally arrive at the memory controller saying that, okay, my caches are completely useless now. Can you give me the data from the main memory? And at that time, what you would see that, oh, you know what, somebody has already started requesting the data from the main memory itself. So you would just simply quietly stay there. And once the data comes back, you would just simply return the data back to the core. So it's again, this off-chip prediction is a latency hiding technique. It's working not exactly on the same direction as prefetching, but it's essentially saying that, okay, I'm going to exploit the fact that in modern processors, your cache hierarchy is getting bigger and bigger. So that means it's also getting slower and slower, right? Access latency is getting bigger. So that means we have a possibility to cross-cut this cache hierarchy, go directly to the DRAM, fetch the data, and again hide the latency from the processor's perspective. So that's what we are going to do in this work, off-chip prediction. It's called Hermes, accelerating long latency load request via Perceptron-based off-chip prediction. We have presented this work in last year micro, which we got the best paper award also. So if you're interested, definitely check out this paper. This is also, the implementation is open source, and as I'm going to show, this is using some sort of, let's say, machine learning technique, right? But not exactly reinforcement learning, but here it's a perceptron-based off-chip prediction. So I'm going to discuss like what exactly is a perceptron and how exactly we use it in this context. Okay, so let's go into make a deep dive here. So as I said, like the long latency off-chip requests, they are the main culprits, right? So we are doing all these things, right? So to save our processor from these culprits inside, right? So our prefetcher is doing what? Prefetcher is saying that, okay, off-chip request, I'm going to predict beforehand so that I can fetch it on chip, so that when the demand request comes in, it doesn't have to go to the off chip. It would just simply find it on chip. But then, unfortunately, a lot more requests eventually goes off chip also. And if it goes off chip, so it creates problem. It creates what problem? So it often stalls the processor by blocking instruction retirement from reorder buffer. So if you're not familiar with reorder buffer, that's also fine. But then reorder buffer is essentially a structure that is quintessential for maintaining the out of order execution. And virtually more of all the processor, or let's say like many processors that you interact with day-to-day life, right? So they're most likely that they are out of order process. So they have something called a reorder buffer, and then if your reorder buffer gets full, then you cannot essentially like fetch new instructions. You cannot do out of order execution, and the entirety of the mechanism stops basically. Okay, so essentially, if you have long latency off chip load requests, they often stall these processors by blocking this instruction retirement. Instruction retirement means you can think of this as a queue, right? So if you do not retire from the reorder buffer, so it's basically that this the stage essentially gets blocked at the beginning, right? So you cannot pop out something from here. So eventually that would back propagate, and it would make the entire ROB full. So that means you cannot also put something inside the ROB also. And at that time, your process simply stalls. There is nothing left to do. Okay. So we are essentially trying to reduce this as much as possible because they limit performance, right? So that's the severe limitation of the performance. Now, to alleviate this challenge, right, that this blocking the instruction retirement from the reorder buffer. So traditionally, architects have actually relied on two kind of, let's say, key techniques, which we have covered before. I'm going to reiterate again: caching and prefetching, right? So we deploy sophisticated prefetchers solely for this purpose, that when the data is required, it's not going to go off chip. And we also have, let's say, large on-chip caches, right? And we are increasing those on-chip cache sizes also. I'm going to show you, let's say, what's the trend there looks like how the processor have, traditionally increased the cache sizes and what effect it has in terms of, let's say, memory access latency. So this is, so the first, let's go back to the first observation. So the observation is like, if you have sophisticated prefetcher, what happens there? So even in presence of sophisticated prefetcher, like in this case, we have examined Pythia itself, right? Even in presence of Pythia, many loads are still going to off chip. What fraction? Exactly, let's say, like a little bit of 50%, more than 50% is successfully prefetched. For every aspect, you can think of it as like almost 50%, right? So 50% of the requests that are supposed to go off chip, if Pythia was not there, they are not going off chip now, but then the remaining 50% is still there. That's essentially the culprit. Okay. Now, out of this 50% that are still going to off chip, even in the presence of a state of the art prefetcher, 70% of them, right? 70% of this 50%, they actually block the reorder buffer from retiring, oldest instruction. So this like dark red pie, right? It's even the bigger problem. So we are trying to alleviate that challenge as much as possible. Now, if I look into those 50% of the requests that are still going to off chip, and I'm going to see, let's say, how their latency is visible from the core, right? So because they are going off chip, prefetching is not useful for those requests. So what happens in that case? If you need to access the main memory, your latency looks like this. You access L1 first, then you access L2, then you access LLC, then you have main memory. So the entirety of the latency is exposed to the processor. Now, the observation is that if you try to access this main memory as fast as, let's say, when you generate the request, right? So that essentially in parallel to the cache lookup, then you can actually save the latency. Save the latency by as much as 40% of the stall cycles can be removed if we remove the on-chip cache access latency from the critical path of this request. So that's the key observation here. So that if we go from this timeline to this timeline, so there is saved cycles. Okay. So now the problem here is essentially that L1, L2, LLC access lookup latency by itself is also huge. And the trend shows that this is not going to be, slower in any time soon. So this is what we, cited, like some couple of like studies from at least 1 decade earlier, right? That from 1990 to 2010. So here you can see that on-chip cache sizes, they are increasing in a pretty, stable rate. And the hit latency also is increasing pretty stable rate, right? So that's a study that has been done on 2007. Now, if you look into more recent processors, right? So this is Intel's Skylake all the way up to Raptor Lake, which it came out in 2022 itself. There also we are seeing that the L2 size and the L2 latency is going increasing pretty steady rate. So yeah, and the funny part is that by the time we are actually we have incepted the idea, and Golden Cove was the let's say state of the art microarchitecture at that time in 2021. Between that time and the time that we have presented this paper, after getting accepted to the conference, finally making the presentation, they have like doubled the cache. It's like from 1.25 MB of per core all the way up to 2 MB per core. It's like by that time itself, you have increased, and your latency has also increased from 15 cycles to 16 cycles. So this trend is, we posit that this trend is likely going to continue. Why? Because in the end, these bigger caches also make difference in performance, because the workloads that you are going to execute in these processes, their data size is also increasing, like by quite a lot margin. And no matter how big your caches are, they are like your data set size is likely going to be way bigger than this. So the designers, they have a reward in this case to increase the cache sizes also. So it's intuitive to make to understand like why they're increasing the cache sizes at steady pace, but then that also has this downsides, that we are increasing the latency. So that brings us to the goal of this paper, that our goal here is to improve the processor performance by removing this ever increasing on-chip cache access latency from the critical path of the off-chip load. So basically, your request would still go to off-chip, start fetching the data, but at least you would start fetching the data from the DRAM as soon as possible. You don't have to wait for this cache lookup to finish, and then only you would start fetching the data from the cache. Okay, so that's the key idea here. So towards this, we propose Hermes. Hermes is based on two key ideas. So first, Hermes predicts which load requests are likely go to off-chip, and for those predicted off-chip loads, it would start fetching the data directly from the main memory, while also concurrently accessing the cache hierarchy, as I just said, right? So now let me give you, maybe before going into the full pictorial diagram of Hermes, let's see what is the key contribution of Hermes. So Hermes employs the first Perceptron-based off-chip load predictor that predicts which loads are likely going to off-chip by solely learning from multiple program context information. And so this is like a adaptive learning technique that uses Perceptron, and I'm going to show how exactly it uses Perceptron. Okay, so now let's see like how Hermes improves performance, right? So this is a traditional let's say processor like diagram, right? So you have core followed by the L1 data cache, then L2 cache, LLC cache, then you have memory controller, and then you have the off-chip main memory. Okay, so now in the traditional system, what would happen is that you would request, the core would request the data to L1D, misses L2, misses LLC, misses memory controller, and then finally access the off-chip main memory. Then it would return the data back to the core. So that's the timeline, that's how it looks like. So in the baseline case, you would have L1 followed by L2 followed by LLC, and then the main memory. Now, if your processor has big enough, let's say, instruction window, right, the reorder buffer, that's what I just mentioned before. So your processor can actually hide some part of its latency, hiding in the sense that it can say that, oh, I'm waiting on that data to come back. At the same time, I'm also going to explore some other instructions if I can execute them or not. So that's the instruction level parallelism that reorder buffer exploits. But then after some time, the reorder buffer would also get full, and then you don't have let's say any further look ahead to left for you to see new instructions that can be executed irrespective of the instruction that has already missed and then went to the main memory. So at that time, the processor would start stalling. Okay. Now, what Hermes does is Hermes essentially proposes a Perceptron-based off-chip load predictor called Puppet. So for every load request that is generated by the core, Hermes would first consult Puppet to say, okay, tell me whether this is likely to go off-chip or not. If Puppet decides that if Puppet makes a prediction that it's likely go off chip, then what would do, it would, Hermes would simply look up the L1 data cache. Why? Because, there is this, gap also, that you cannot directly access the off-chip main memory using the address that the code generates, because the code generates, probably you would know this, but I'm just going to reiterate, the code generates the address which is we call virtual address. But then, any cache beyond L2, inclusive, like L2 and beyond, any memory structures, they are actually physically addressed. So physical, that's a conversion between virtual address space to the physical address space that needs to be happening. Okay, so that happens in parallel with the L1 cache lookup itself. So that's why Puppet, Hermes needs to wait for that address translation to finish, which happens in parallel with L1. And then once you have the physical address, then what Hermes does, it essentially issues a request directly to the memory controller to start fetching the data from the main memory. Now, in the same time, it is also, the main request is also accessing the cache hierarchy. So it misses L2, comes out to LLC, misses LLC, comes out to memory controller. At that time, it would just simply wait for this transmission to finish. Once this transmission gets finished, then it would just simply return back the data to the core. So in the meantime, what happens is essentially you have started accessing the main memory almost in parallel to when you are accessing the L2 and LLC. So you save this latency completely. So now your processor is seeing this to this. That's the end-to-end latency the processor is seeing. So you save that many solve cycles. In the end, what we are showing here, that your processor might still end up stalling, because the overall latency that you are still seeing, the processor is still seeing, is beyond the limit of the latency tolerance limit of ROB. But still, at least the amount of cycle the processor is stalling is lower than the baseline system. So that's the performance improvement that we are getting. Okay. So do we have any question till now here? Is this methodology clear? Like how exactly it works? Okay. So if that's the case, then, the predictor gets trained when the predictor gets trained when the request returns back to the core. And then, we would train this Puppet predictor. So Puppet predictor essentially resides inside the code itself. Okay. So now let's try to see how exactly we define and design the Puppet predictor. Okay. So Puppet is essentially designed as a multi-feature hash perceptron model. So this is the model that we have not so they have this paper essentially introduces this model, right? As you can see, it's coming from 2005, but we are going to use this model in a different use case, let's say. So that's the off-chip prediction that we are going to use it for. So what does this model do? It says that, okay, each feature, so we are going to learn which memory requests are going to off-chip based on certain features. Okay, features like, let's say, oh, what is a PC program counter value, like the instruction program counter value that is creating this memory request? What is the cache line offset that memory request is going? So that's PC plus offset. You can think of like lots of features. And in the paper we have mentioned, like I think we consider 16 features from the set of features, right? And then we prune down. We say that, okay, some features are not useful than the others. So we are going to, design this model with, a minimal version of features set at in the end. So for each feature, this model has its own weight table, right? And so the weight table, you can think of these weight tables as the space that shows the correlation between the feature value and the off-chip prediction. So you can think of these each individual weights as, let's say, let's say 5-bit number. So 5-bit signed number. So signed number in the sense like it can go from -32 to +32, right? So if the value is, let's say, -32, that essentially means that you have a negative correlation. If the weight value is +32, that means it's a positive correlation. If the weight value is 0, that means that feature is not correlated with the outcome at all. So any feature in the end that shows most of the weights as, let's say, near 0, we can actually prune that feature. We can say that, oh, that feature, like seeing that feature, there is an equal likely probability that we are going to either see a load request that is going off chip, as well as the load request that is not going off chip. So that's what gives us the near zero weight, right? So there is a equal probability of seeing off chip request as compared to the probability of seeing non off chip request. Okay, so let's see how this predictor makes a prediction. Okay, so the prediction happens using simple operations like table lookups, addition, and comparison. So how it happens? So when you have a new load request, we are going to extract Hermes is going to extract features from the load request itself. Feature can be, as I said, like PC value and offset. Like I'm showing an example here, right? So 7FFE0 plus 12. Like you do this addition and then hash it down. You can take a look at the paper itself, and then we show like how exactly we are extracting these features. And similarly, this is one feature. You can have like multiple features. So once you extract these features, you would use this feature to hash it down and use the hash value to index the weight table. Like for example, this feature gets hashed down and then creates the hash value 42 that we use this as an index to look up this weight table. Similarly, you would use the second feature to look up the second weight table, third feature, and then like this. Okay. So each individual table lookups is going to give you individual weights from this table. Once you get the weight, you're essentially going to summarize all the weights. So in this case, let's say the first weight table is giving you -4. Second weight table is giving you 12. Third weight table is giving you -5. So you're going to add all of them. So that becomes 3, right? So then we have something called an activation function. So if you're familiar with, let's say, machine learning, so this is kind of, let's say, you did some like a sum pooling kind of thing, right? And then you're going to do an activation. So activation in this case is a very simple greater than operation. We're saying that, okay, we have some activation threshold, which is again statically set at design time. If your sum of the weight is higher than this activation threshold, you're going to predict that, oh, it's going to go off chip. If not, we are going to predict it's not going off chip. Okay, so that's the key idea here. So if you see this, let's say weight values, right? So the weight value negative means it's essentially negative correlation, right? So it says that, okay, when this feature appears, there is a negative chance that it's not going to be, let's say, there is a chance that it's not going to be off chip. Similarly, this feature, if you're seeing a value of 12, that means there is a strong chance that this feature value is likely going to see an, let's say, off chip request. Okay. So now let me give you an example on how we train this predictor. So then that would make this, this technique a bit more clear to you. So now let's say, let's take this example as a consideration, right? So you have, let's say 4, 12 and -5, and then that gets summed up to 3. 3 is higher than -2 as an activation threshold. So you are going to predict that the load would go off chip. Okay. Now let's say that in reality, the load didn't go off chip. So that means we have made a wrong prediction. So we have to fix our weights in some way. So how would we fix this weight? So let's backtrack our steps, right? So why did we predict that it's going to be off chip? Because it was higher than that. Your sum of the weights were higher than the threshold. So the first step correction is that your sum of the weights should not be higher than the threshold. So it should not be activated if you want to rectify this prediction, right? So that essentially means your sum of the weight is higher than the activation threshold. So you need to reduce the weights. So you take a step back. So you say that, okay, so if your cumulative weight was lower than the activation threshold, so let's reduce the weight back. So what would you do in this case? You again use the same features that you have used in the time of making the prediction. Look up into these weight tables, and each individual weight you're just going to decrement. Why? Because that's the direction that we have to go. Because in the end, we actually saw that it's not going to be off chip. So that means your your threshold should have been, your sum of the weights should have been lower than the activation threshold. So you just simply decrement. So now you can think of the other way around also. So you made a prediction and that prediction was correct. Let's say it indeed goes to off chip. So that means what you did was correct. That means your activation threshold was indeed correct. So you either can decide that, okay, if I have already satisfied that activation threshold, maybe I don't need to increment. But let's say if your prediction was different in this case, let's say you actually went off chip, but then your activation did not happen. So that means your weights were actually, cumulative weights were actually lower than the activation threshold. Then you are going to increment these values. Does it make sense? It's like simple increment and decrement operations with lookups, and you can just simply train this model. And this training, just like the reinforcement learning also, this is not exactly reinforcement learning, but this training also happens online because we can afford to happen it online. It's just simple index lookup, and it's just a increment and decrement operations. We are not also entertaining, let's say, if you read the paper, we are not also, making this weights to be fraction, so that, fractional addition, fractional subtraction is taking much more complexity, right? It's simple integer weights, even small integers like 5-bit signed integer or 6-bit signed integer, and it works. That's what we show here. Okay. So yeah, I mean, this sort of model is, as I said, like, we have not actually come up with this model by ourselves. We probably have tuned it for our case study. But so if you're really interested in this sort of models and use cases of such models in computer architecture, right? So there are lots of other works that people have explored these sort of models into different domains. Like, for example, people have used this hash perceptron. Predominantly, it was introduced for making branch prediction. So you can think of this Boolean value as branch prediction, right? So you have said that the branch is not going to be taken, but eventually it was taken, or the vice versa. You can just backtrack and train your predictor like this. Similarly, they have used it also for cache replacement policy. Like, for example, they have used it for identifying dead blocks. Dead blocks in the sense that those cache blocks inside the cache are dead. So you're going to query this model saying that, okay, given this request that I'm going to place to the cache hierarchy now, tell me whether this request is, tell me whether this cache block is dead or not. If the predictor says that, you know what, it's dead. Dead in the sense nobody is going to, touch this cache block later on. Is the one that you are, servicing now, that's the one that's going to use it. There is no point in putting the data inside the cache block, inside the cache. Then you are simply going to, bypass the cache. So in that case, also people have used this sort of, prediction mechanism for, making accurate dead block identification. And if you can think of any other use cases, that would be even, like novel in that sense that, you can use certain, use cases where you can exploit the similar structure to make really accurate, let's say, predictions in those cases. Okay. So now let's see the performance improvement of this work. Yeah. So here is the single core performance improvement of Hermes as compared to the state of the art prefetcher PTR, right? As I said, like, Hermes is not exactly like a prefetching solution, right? But it does do latency hiding. So in that sense, it's not that bad, right? So Pythia, and when you explicitly consider that, Pythia has a area overhead, like the storage overhead of 25 KB, and then Hermes only has a storage overhead of 4 KB. So that's like in 1/5 of the storage budget, you're almost, bridging more, like 50% around performance benefit, right? So that's not that bad. The beauty is, if you, so that's what I just said, that it gives almost nearly the 50% of the storage, 50% of the benefits of Pythia with only 1/5 of the storage overhead. But then the beauty is that if you add both of these together, then that adds 5.4% more performance benefit even on top of the complex prefetcher like Pythia. So that gives the most bang for the bucks. It's like, I'm going to do off-chip prediction as well as I'm going to do the prefetch standard, traditional way of prefetching. So that's the benefit there. And if we evaluate, let's say, an ideal version of Hermes, ideal in the sense that magically you know which requests are supposed to go off chip, magically. So you are not essentially getting bounded by the predictions accuracy, predictions coverage. You essentially know like which one would go off chip. And in that case also, our online implementation, the predictor implementation, is nearly coming 90% of that ideal version. So we are also, really good in terms of an idealistic predictor in that sense. Okay. So now, if we also take a look at, let's say, what fraction of load request, so what fraction of memory requests are getting increased in the DRAM. So you can think of, Hermes always has a sense that, oh, I'm going to make a prediction whether it's going to go off chip or not. So what if I make a wrong prediction? So I made wrong prediction in the sense that I predicted that it's going to be off chip, but in reality it didn't go off chip. So in that case, what would happen is that I'm sending a request to off, DRAM unnecessarily, right? So, and fetching the data from the DRAM, and that essentially, creates latency problem in the DRAM side. That is that also, let's say, increases the DRAM traffic, bus traffic, which is also energy, right? So that's something that we need to consider. So here we are actually plotting that data. So it's a percentage increase in the main memory request over the no prefetching system, and let's try to see how it looks like. So as you can see, like if you only do Hermes, that gives you, let's say, 5%, 6%, more requests than the baseline. Like if you don't do any prediction, just simply go. You don't have a prefetcher also. But then the thing is, if you have Pythia, that actually gives you almost like 38%, increment than a no prefetching system. So that essentially means that Pythia actually provides performance benefit, but it also increases your main memory transfers because it's a prefetcher, right? So it also has its own, let's say, accuracy. So all the cache lines that it's predicting to be likely be accessed by the processor is not actually accessed by the processor. So that's what getting incremented here, right? But then again, like if you add Hermes on top of Pythia, then that increases, the DRAM transfers only by 5.9%. Now, if you look into this numbers and then put it into the perspective of the performance benefit that these numbers are getting, right? So, like you're getting literally 11.5% performance for 5.5% increment. You're getting 20.3% performance with 38% increment of DRAM traffic, and then additional 5.4% performance by only 5.9% DRAM traffic improvement. So it gives you a picture that for every 1% performance benefit, the tactics these three tactics that we just discussed, right? If you look for Pythia, that for every 1% performance, it increases the DRAM memory transfer, DRAM request by 2%. If you implement Hermes on top of Pythia, that gives you, like, for 1%, you already are on the, let's say, break-even point, right? For 1%, you're on 1% increment. And if you implement Hermes alone, that actually even better in terms of, let's say, sensitivity. So what it essentially shows that Hermes alone might not give you the entirety of performance benefit of what Pythia can provide, but it's much more efficient for the same amount of, let's say, DRAM transfer that it's doing. So that alludes to this situation that if you're designing a processor that has, let's say, memory bandwidth is a scarce resource, you have to consider this from the get-go, then implementing Hermes alone might be a better design choice for you as compared to implementing Pythia. Or if you can afford all of them, then probably, just implement all of them. So that's what the key takeaway here is, that Hermes is much more bandwidth efficient than even a bandwidth efficient prefetcher like Pythia. That's the takeaway. So we showed it here also. And yeah, I'm not going to too much detail into this thing. So what was the takeaway here is that if you look into the performance here, right? So the Hermes performance, Pythia performance like this. And then if you implement both of them together, then it outperforms in both the cases. And we have also evaluated Hermes for not only on top of, let's say, Pythia as a prefetcher, but we also checked, let's say, other types of prefetching algorithms also, because somebody can say that, oh, you know what, like maybe Hermes is providing additional benefits on top of Pythia, but what if we implement it on top of multiple other types of prefetching? Does it still hold true, this performance benefit? The answer is yes. So if we see that if we have Pythia, then adding Hermes on top of that Pythia, it's giving you 5.4% performance. But if you add it on top of the other prefetcher like Bingo, you have 6.2, SPP you have 5.1, 7.6, 7.7. So we have a healthy performance uplift on top of any baseline prefetcher that you can think of, or at least any baseline prefetcher that we have evaluated here. Okay, so that's the key takeaway here. And then in the end, we have, like, as I said, like it's a very modest storage overhead, only 4 KB, and it's only consumes let's say 1.5% power overhead as compared to a Alder Lake type performance core configuration. And so that's to summarize everything that I have just said till now. So essentially, Hermes advocates for off-chip load prediction, which is a different form of speculation than the load address prediction employed by prefetchers. So that's what I want you to have a key takeaway, right? So prefetcher essentially does this load address prediction. It predicts like what address its program is going to access next. We are looking at some sort of a different variation of that prediction, but the overarching goal is the same. We're essentially going to hide the latency. That's it. It's just how we are approaching to that problem. Okay. And we showed that off-chip prediction can either be applied by itself, or it can be combined with the load address prediction to provide additional performance benefit. So in the end, we proposed the first Perceptron-based off-chip load predictor that has decently high accuracy, high coverage, low storage overhead, as well as high performance benefit over the base prior baseline, and high performance benefit per bandwidth also, which we just showed. But that said, I still believe that this accuracy and the coverage is not good enough to be implemented as is in the product itself. So we are in talk with some product development teams who are interested in implementing Hermes-like solution in their actual product. But what we believe essentially that if we want to push it for a product, then probably we have to still push this accuracy, because every inaccurate decision essentially means that we are going to exercise the DRAM, and that DRAM transfer is way more power consuming. So that's why we are seeing here, right? So when we showed it actually has a power overhead. So if you're designing a processor based on power in mind, right? So you probably this might not be a, let's say, attractive solution for you. So that makes me believe that we still have some sort of, let's say, leeway left, which innovation left here. And for that reason, we have also, open source this like infrastructure. And it's kind of, let's say, built on top of the same infrastructure that we used for Pythia. And it's inherently has like all the workload traces that we have evaluated this work on. And also you have, let's say, 13 types of prefetcher out of the box, right? So you can, and I'm just giving you a hint, right? So you can use this infrastructure to, solve, do your lab works also. So you would be asked to, implement new prefetchers. So you can take a look at these implementations also. Okay. So in this directory, you can get, like, let's say, all sorts of, prior prefetching works. As you can see, it goes back all the way up to 1992 to, let's say, 2021, right? So that's like pretty wild. Yeah. And then you would also have, let's say, 9 off-chip prediction algorithms implemented pretty much out of the box. And it's also, the interface is, let's say, extensible enough that you can simply have your own predictor implemented, and the framework would work pretty much out of the box. So if you are interested in this direction, definitely do check out our GitHub repository, as well as if you have any further ideas, I would be happy to discuss, because these directions are like fascinating. I mean, it literally fascinates me. And as I said multiple times, and probably you would hear this in Professor Mutlu's lecture in prior incarnation of this coursework, right? That memory systems they were problematic before, they are a source of problem now, and I would proceed that they would be, source of problem in the future systems also, if not more than what we are seeing now. So that makes us believe that we need to innovate in this direction. So, and this is just a, like a legacy that we are seeing, right? That we have like so many, prefetching techniques that has been explored from like over a long period of time. And then still we are not there yet. So keep on thinking on this direction and as you can see, like, machine learning based or let's say data-driven based architecture can solve things more intelligently in these cases. So yeah, if you have any other let's say directions, definitely reach us out. Okay, so then the next stage is the execution based prefetching, but maybe we would stop here for some time, and let's meet again at, yeah, let's take, let's say, 10 minutes break, and maybe we can start at 3:15. Okay, perfect. Okay, so let's start from where we left off. So we have seen like some advanced prefetching algorithms, right? The RL-based prefetching, and then we have also briefly touched upon the off-chip prediction. So now we are going to go on a different, let's say, gear now. Okay, so this is what we call a different type of prefetching, which we have alluded to yesterday also. So this is what we call the execution-based prefetching, and as you would see, this is also something very close to us as a group, because Professor Mutlu has his PhD thesis on this direction. And as I'm going to also discuss that his thesis, his PhD work also got Test of Time Award, which is like a really big award in a sense that it has stand the test of the time, right? So it has been implemented in multiple processors. It has proven to be, let's say, independently verified, and all of these things, right? So they have like practical impact in that sense. And even some, let's say, enhancement of these works since the Professor Mutlu's first work on 2003. This is 2023, so that's 20 years after this micro. We also have a best paper award which is on the same topic. So it's just fascinating, like 20 years, still the old problems are the problems now. So let's see. Okay, so execution-based prefetching is kind of, let's say, different than the traditional prefetcher that we have, talked about before, right? So we have talked about software-based prefetchers, we have talked about hardware-based prefetchers, right? So software-based prefetchers essentially says that, okay, I'm going to, either programmer or compiler is going to insert certain instructions. Those instructions are software prefetch instructions. They are going to get executed throughout the pipeline. And the whole goal of these instructions are to fetch the data from the wherever the data resides to the cache hierarchy, right? So that's the software prefetching. Hardware prefetching says that, okay, I'm going, so the prefetching request is, the prefetch request is going to be initiated purely from the hardware itself. So it's transparent from programmer's perspective, transparent from the compiler's perspective. So it's much more, let's say, the binaries that you're getting is much more, or let's say the prefetching solution that we are getting is much more, let's say, dynamic, in a sense that you don't have to, worry about, re-optimize your code. If you do software prefetching, if you exploit software prefetching, you don't have to re-optimize your code from, let's say, if you're running in processor X as compared to running in processor Y. Okay. So execution-based prefetcher is another class of prefetcher in that sense. So the idea here is that we are going to pre-execute a piece of the program itself with the sole purpose of prefetching the data. That's it. So hopefully we are going to, as I'll show, right? So either we can execute the entirety of the program, that's a piece of the entirety of the program, or we can also have a narrowed down view. That's okay. If I'm going to target certain, data structure accesses, let's say I'm going to traverse a linked list, right? So, and then certain data structure access of that linked list is the problematic one that is never going to be found. It's likely not going to be found in the caches. Then what we are going to do is we are going to say that, I'm specifically going to execute those instructions that leads to this memory miss, right? So not the entirety of the program, not the entirety of the loop also, but only those instructions that leads to this memory miss. And then I'm going to execute it speculatively, hopefully running way ahead of the actual execution, so that the sole purpose of this pre-execution is to fetch the data to the cache hierarchy, so that when the actual execution finally catches up, then you would already have the data inside the cache hierarchy. Okay, so that's the key idea here. So as I said, that only need to distill the pieces that leads to cache misses that I just discussed, right? So here we have some sort of, let's say, idea called, let's say, speculative thread, right? So you can think of this, let's say, execution context that are getting executed, that are running ahead, right? Running ahead of the actual program execution is, let's say, speculative thread, right? So it's like a execution context that is running ahead. And now the speculative thread can be executed either on the, like, a separate processor core. Like, for example, you have, let's say, 4-core configurations in laptop, right? Let's say, or maybe, server processors have like lots of cores, right? And maybe many cores are staying idle. So in those cases, you can actually use those idle processor cores, or maybe idle processor altogether, right, in a different chip, right, to execute those speculative threads. Or you can use, let's say, the hardware thread context, like if you have SMT enabled, like say simultaneous multi-threading enabled, right? So in those cases, you can use the other thread that is mapped to the same core to execute this speculative thread, right? Or maybe you can say that, okay, I'm going to execute in the same thread, same context, and like same core, same thread, just by utilizing an idle cycle. So let's say if my the actual execution is waiting on the data cache miss, then you are not doing anything anyway, right? I would just simply steal those cycles and run my speculative thread. So that's the three ways of executing these threads, right? So now we have to define some let's say questions. Like the first question that we have to answer is that, okay, speculative thread is like cool, sounds good, but then how on earth we are going to construct these threads, right? So there are like it seems that there are multiple options possible, right? So we can use some sort of like just like prefetching techniques, right? So you can have, let's say, software based pruning and spawn instructions, right, to generate the speculative threads, right? You can have like hardware based pruning and spawn instructions, or you can have, let's say, you can have the third option, which is we are not going to create a separate thread per se. We are just simply going to execute the original program itself in a different fashion, uh, execute it faster and speculatively, so that we can run ahead. So run ahead execution essentially falls into this third category. It's like we are going to execute the same program code, but in a speculative way, much faster, so that it can run ahead of the actual execution. And the whole goal, the sole goal of this run ahead execution is to generate the memory request, prefetch that data to the cache hierarchy, and that's it. So there is no correctness concern. There is no, let's say, I'm going to come next. So let's go one by one. So yeah, so as I said, like, okay, that's the next one. So speculative thread, the sole goal is to discover the misses before the main program. And so basically, so that the main program kind of avoids waiting on or stalling on this the request that your speculative thread is fetching. Okay, and then the idea here is that to get ahead of the main thread as much as possible, but not to execute it correctly. So you don't have to so the whole goal here is to execute as like run ahead as much as possible. So even if you in doing so, if you, let's say, face some instructions that you don't know what would be the value of it, right? Then you can just simply either go speculatively, or you can just simply say that, okay, I'm not going to execute those instructions, but let's try to execute something that we can execute. So it's essentially like a best case, let's say, execution, right? So you just simply skip on, do whatever that you can execute, and do your best to generate as much memory request as possible beforehand, so that when the actual program finally catches up, you would be seeing that those data are present in the cache hierarchy. Okay, so yeah, so as I said, like it's completely going to be purely speculative. So there is no need for recovery of the main program, even if the speculative thread is incorrect. Like even if you have, let's say, a software based tuning, and then you're executing this creating a new execution thread, right? There is no guarantee on the correctness of that speculative thread, because we are not like, that's not what the program is executing. Your program would eventually execute, go there when it executes, like that's the main execution. These speculative executions, they have the entirety of the goal is to generate, aid the main execution, so that we don't have to recover, like worry about their correctness, worry about the recovery of the main execution context also. Okay, so that's the key difference, and you should always keep this in mind. Okay, so here is the first few walks that have explored this direction, right? So as you can see, it dates back all the way to 1998, right? Assisted execution, simultaneous subordinate multi-threading, execution-based prediction using speculative slices, and so on and so forth. And this is a beautiful, let's say, a really nice depiction of what exactly is going on here, right? So as you can see, so this is the main execution context, right? And I'm going to explain more about the speculative execution threads in terms of, let's say, load prefetching, right? But then they can also be used to aid branch prediction problems. So let's say you have some sort of hard to predict branch, right? So on Earth, you cannot ever, it's highly unlikely to, predict very accurately what's going to be the direction of this branch, whether it's going to be taken or not taken. So what you can do, you can say that, okay, I'm going to fork a bit beforehand, saying that, okay, I'm going to create a speculative execution thread here. I'm going to execute it, these instructions here, as much as possible. Like I'm just going to, go, forward in time. The goal is that if you can somehow come up with the instruction that feeds this branch, right? Let's say the branch is a data dependent branch. Let's say if you have written some code like, okay, if AI equals 0, then only you are going to do this. Then AI equals 0 is what? Like you have to load the array of I, right? So that's a memory load. And only when you have completed that load, then only you can check the load value with the 0 value. If it is the case, then you are going to access it. Otherwise, you are not going to, either you are going to take the branch or you're not going to take the branch. So the goal here of this, speculative execution is to get those data as fast as possible, so that at least when the branch would finally be executed by the processor, your outcome would be ready. So that's the idea here. Similarly, if you see from the cache perspective, from the prefetching perspective, it's also the same thing, that you're forking out a bit beforehand so that you can generate this cache miss. So by the time when the program actually reaches this load instruction, hopefully your cache miss would be completed by this time. And when the program actually demands for the data, it's already present in the cache. So that's the key idea here. Okay. So we're going to go a bit deeper into this thing. So as I have said, like this pre-execution based thread-based pre-execution, they can be the thread can be spawned inside the hardware, the thread can be spawned by the software itself. And then we are going to so in the next we are going to essentially discuss like what are the key problems that we have to solve in this method, right? The pre-execution based thread-based pre-execution. So we have to answer these three key questions. So where to execute this pre-computation thread, as I have alluded before, right? So you have different options. So you can either execute saying that, okay, I have some core that is not used, so probably I'm going to use those cores. I have some processor altogether, let's say in a different socket that are not used, probably I'm going to use those. I have, let's say, some threads inside, like the execution context inside that same core itself. So the SMT thread that I have mapped to the same core, the SMT thread, one thread is running ahead of the main actual execution context. The goal is that whoever is running ahead, that's going to fetch the data for me. That's going to resolve the branch for me. It's basically aiding the main execution context. That's the idea. Or maybe we can say that, okay, we are going to execute in the same core, same context, but obviously we cannot stall the main execution also, because that's the whole goal of improving the performance. If you stall the main execution for aiding the main execution, there is no point. So you have to wait for the opportunistically finding cycles where the main execution context is, let's say, idle, is stalling. Then you can use those cycles for executing the speculative thread. Okay. So the second question that we have to answer is when to spawn this pre-computation thread. So the answer is that okay, maybe we can insert the spawning instruction well before the problem load. Then the question is like, how far ahead? Like if we go back to this thing, so where exactly we want to fork? If we fork too ahead, then by the time, let's say, this cache would like this data would come back to the cache, by the time it would be used, maybe it would have been kicked out from the cache itself. Similarly, if you do it late, let's say, so if you do it late, then probably the processor has already demanded the data, and then you are not probably running early enough. So that's what we need to decide also. And then the third question that we have to answer is like when to terminate the pre-computation thread. So either we can do like a pre-inserted cancel instruction, or maybe we can do based on some sort of feedback mechanism saying that, okay, I have historically this speculative thread has generated accurate request, accurate prefetches, then probably I can run it a bit long enough, or if it is inaccurate, then probably I can throttle it down. So that's the idea here. So here is an example of early work on tolerating memory access latency through software-controlled pre-execution in simultaneous multi-threading processes. So as you can see here, it's a pictorial example, right? So you have the main execution that is traversing a linked list, and then you spawn the speculative thread. That sole purpose is to traverse this linked list. So you're not going to fetch this data back to the core because those are speculative threads. The only thing that you are doing is you are just fetching those data from, hopefully, let's say, the main memory, just putting it into the cache, so that when the main execution finally catches up and tries executing those, fetching those nodes, you would already find it there. Similarly, you can think of it as, let's say, multiple procedure calls also. Let's say you are accessing this function, and your speculative thread can be spawned to access, run ahead and execute these functions as speculatively as possible, so that when you finally end up executing this, you would see that, okay, lots of things are already inside cache. So it's acting as a prefetcher for the main execution context. Okay, so here is an example of it's a big example from that paper itself, and it's coming from a Spec 2000 benchmark NCF. It's still there in 2017 version of this benchmark also, and it's notoriously difficult to prefetch because of this sort of let's say like a pointer chasing application, because it's a like a linked list traversal. So and it's notoriously difficult even in today's like prefetches. So I'm not going to do too much detail into this. So you can take a look at this. But essentially, what it does is basically it tries to target this while loop, and it's trying to create a run ahead loop that is going ahead. So it's a pre-execute start and pre-execute stop. So that's the run ahead loop. Okay. So it's basically running ahead of the main execution, so that when the main execution finally catches up, it would see the data inside the cache. Okay. But in this case, what obviously what you can see is that we need the ISA extensions, right? Because we need these instructions like pre-execute start, pre-execute stop, pre-execute cancel even, right? So these ISA support needs to be there to launch these threads from the software itself. And as the paper showed that the work essentially reduces the latency by quite a lot. So for each workload, you are seeing the 2 bars, right? And then the top of the bar is basically the reduction. So it's normalized to the normal out of order baseline, right? So that's 100. And you can see that lots of bars have reduction. But at the same time, you also have some workloads that are increasing reducing the performance. So it's basically taking more time here. Why is the case? It can be for multiple reasons. So one reason can be, let's say, the prefetch request that you have generated inside that execution, speculative execution context, right? They're probably worthless, right? So you have no benefit from there. So in that case, this might be possible, or it might be possible because of, let's say, you are executing too many instructions, right? So maybe just because you're executing so many instructions to even find, let's say, useful data that you can preload, you're probably losing out opportunities. So how can we, improve upon that? So here is the 2 works that actually improves upon those things. So as you can see here is that, so this is a while loop condition, right? So that's essentially also like a branch instruction, right? So it's going to be either going inside or not based on this condition. Right? And then you can see here is that this is also a data dependent branch. So you are going to traverse this data structure heap and going to access this cost, and based on this value, the outcome of this loop is going to be dependent. So it seems like this is really hard to predict. The branch is also really hard to predict. Why? Because the data itself probably is not present in the cache. So only way to execute this branch would be, okay, first get the data. If you don't have any other pre-execution context, get the data, then compute this instruction, then compute the outcome of the branch. Okay. So now what we are going to do is we are going to say that, okay, I'm going to put a fork point here for this node to heap function. So there was some function. So what they're going to show here is that if you just go and naively try to do the previously pre-execute thread-based pre-execution method, right, that essentially executes the entirety of the program, like the part of the entirety of the while loop. Okay. So it's going to execute a lot of instructions. And not all the instructions are actually making the way to fetch that data. So that data fetching is only happening in this LDS. Okay. So that's the heap I2 cost, basically. This is the load that fetches this data. But then not all the instruction is feeding to this thing. How would you understand which fetch instruction are feeding to this? If you only want to target fetching this data, so see which instruction is feeding that data. So this load is happening from A4, right? So let's do the backtracking. So who writes in A4? This guy writes in A4. What is the input operand? T7. Who writes in T7? You would go backtrack and then try to see who writes in T7. So that's what we call a backward slice traversal. So you first target what you want to prefetch. What do you want this pre-execution context to chase for? And once you narrow it down, then narrow down only those instructions that leads to that cache miss. So that's what they're going to do here. So what it seems that if you want to target this heap cost instruction, it seems that only this 3 instructions is enough to feed to this instruction. So that's what we call the forward slice. So basically, this is backward slice. So that's what we call the execution slice. So this slice is essentially feeding the data to this one. So as long as we are going to execute these instructions as fast as possible inside this loop, we can run ahead way further instead of executing so many rubbish instructions. So that's the key idea here, that we can optimize these implementations, optimize this software-based threads also to selectively execute the instructions that are going to be useful. Okay. Do we have any question till now? Okay. So if not, then we are going to move into the run-ahead execution. So run-ahead execution is also one technique of, let's say, like a pre-execution based prefetching, right? So as would be evident, the more we'd go there. So we need to put run-ahead execution into a bit of, let's say, historical perspective also to understand where run-ahead execution is coming from. Okay. So at that time, the general notion was to create large out of order instruction to create out of order processes with large out of order windows. So essentially what it means, like you have huge ROB sizes, right? So the more ROB sizes that you have, the more, let's say, independent instructions that you can find on from that instruction window, so that even if your processor is stalling on the data from some one instruction, at least you have some ample candidate available there that can be executed in parallel with when the data processor is already stalling for that memory instruction to come back. So that's the whole idea. But then the thing is that if you try to create a wide out of order processor, it's not that easy. It's not that easy in terms of processor complexity. It's not that easy in terms of processor let's say power and area also, because it increases. So that's what the context when the run-ahead execution was proposed. Okay, so it was, as the name suggests, it's an alternative to very large instruction window for out-of-order processes. You can see where they are coming from. Right? So the key idea here is the following: that when the oldest instruction is a long latency cache miss, right? You checkpoint the architectural state and you enter into a run-ahead mode. So this run-ahead mode is entirely speculative. The whole goal of the run-ahead mode is to speculatively pre-execute instruction with minimal stalling, as much as minimal stalling as possible. And the entirety of the purpose of this pre-execution is to generate the prefetch request. And that's it. So your program has started stalling at some point. Instead of going into, let's say, complete stop, you went into something called a run-ahead mode. That's a speculative mode. You're not guaranteeing any correctness of the data. Neither your program is seeing that state also. So as we are going to see that any changes that we are going to do in run-ahead mode, it's completely invisible to software. So once we come out of this run-ahead mode, the checkpoint that we created before going inside, we would actually restore from that checkpoint. So that once we come out of the run-ahead mode, it's as if that nothing happened from the processor perspective. But what happened is basically you have discovered some memory cache misses that you have hopefully already started fetching. So now when the processor would start executing, it would actually see those data to be hitting in the cache. So that's, I'm going to show you, let's say a bit more in the pictorially. So if in the run ahead mode, if you find some long latency instructions, let's say in the run ahead mode also you have found some data, so let's say some memory requests that are again going off chip. Right? So the answer is that, okay, you start fetching the data. Maybe you have found some instructions that are, let's say, dependent on the the memory instruction that for which the processor itself is stalling. So in that case, what you are going to do, you are going to say that, okay, I'm just going to skip through those instructions and saying that, okay, as long as that load on which the processor itself is stalling now cannot come back, I cannot execute this instruction. So let's just mark it invalid and just try to look for some other instruction that we can do, and that's it. So it's like a best effort kind of situation, right? So, and when the original miss returns, like the one that the processor was stalling here before, right, the long latency cache miss, when that returns, then you restore from the checkpoint, flush the pipeline, and resume the normal execution. So after resuming the checkpoint, after restoring the checkpoint, from processor's execution state's perspective, nothing happened. Like that run ahead mode literally didn't exist because it did not make any changes to the processor. But the thing that it did is basically it warmed up the cache so that next time when the processor would start executing now, it would see inside the cache. So here is an example of the run ahead thing. So if you have perfect cache, you have a compute and then you have a memory request. Here is a memory request hit. Life is good. You would keep on doing. Again, you have compute. After certain compute, you would again see a load request. It's a load hit. You would keep on doing. Life is good. But if you have a small window, a processor with small out of order window, then what happens is that you would do the same compute. Then you have a load instruction. It's not a perfect cache also. So yeah, it's a cache miss. So what happens in case of cache miss? So you would definitely start accessing the memory hierarchy, but it would take some time to come back. By the time it comes back, you can still execute for some few cycles more because you have some out of order window left, right? It might not be. So your instruction is the oldest instruction at the head of the ROB, but you have still probably some entries left in the ROB. So you can still fetch some new instruction. If they're independent, you can start executing. If they're independent, you can start executing. Fine instruction level parallelism. But then after some point, that also stops. Then you have no other way than stalling till this miss returns. And your processor can only start when the miss returns. You do compute and voila, you have another load miss. And then the same thing again happens. So life is hard here. If you especially have, let's say, if you make the out of order window longer, then you can essentially make this part of the game, like while the processor is waiting on the load, you can still execute a bit more. And that's what a longer out of order window processor buys you. But then the hypothesis is it doesn't matter how big your processor becomes. At some point of time, you would likely see a ROB stall. You remember if we also talked about this full ROB stalls in Hermes also. It's the same problem that had happened before 20 years back. And it's the same problem that remains today also. So your processor after some time, no matter how big your out of order window is, it starts stalling. So what Runahead does this thing. So you compute and then you have a load miss. The moment you see a load miss, you would do some compute till now, which is this, the compute that the processor is still capable of doing it. But once the processor becomes completely full, your ROB is full, you don't have any other space to do anything. So you switch to something what we call run ahead mode. So this run ahead mode, it's entirely speculative mode. So the whole goal of this mode is that to find this load, to execute this part of the instruction here itself, so that we can at least discover this load to miss in this speculative mode. Now you can also already understand that if this load is dependent on this load, let's say you are doing a linked list traversal, you can only do pointer arrow next. So you have zero idea of knowing what would be the next unless you return from this one. Then you can see that, okay, probably it cannot go through. So that's a downside. So there has been enhancement on run ahead processor also that predicts that, okay, till this load is coming, I'm going to predict the value of the load, so that at least we can make some speculative enhancement here. But the whole idea here is that to explode this explode this load miss inside this run ahead mode itself, so that run ahead mode stays for some time more till this miss one returns. So once this miss one returns, you have to stall for some time. At this time, you are going to, so you have made a checkpoint here. You have to flush everything, and that's the stall time basically, when the processor is flushing everything and restoring the checkpoint. Once the checkpoint is restored, then you re-execute this load one, and now by this time the load one is hitting. So you can go ahead, do the compute. By that compute, your miss 2 is probably ending. And so when your load 2 instruction, the load 2 access instruction finally comes in the actual execution, not in the run ahead mode, in the actual execution, it gets a hit. And that essentially ends this timeline from there to there. So that's the save cycles. So that's the whole idea of run ahead execution. Is it clear? Okay. So yeah, so run ahead execution is essentially, as I said, like, it's instead of stalling during an L2 cache miss, the processor is speculatively pre-executing the program itself far ahead into the actual instruction stream to generate this prefetch request. And hopefully that all the prefetch requests that we are going to generate is likely going to be very accurate, because it's the program itself, right? You're literally executing the program's own code. So there is good chance that when the program finally executes those instructions, they would generate the same data. It's the same address, like they would try to access the same address. So that's the idea here, so that it would in the end generate very accurate data prefetch request. So instruction on the predicted path, predicted program path are prefetched into the instruction cache and other cache levels, as I said, and the hardware prefetcher and the branch predicted tables are trained using the future access information. So all the entirety of the goal is that your caches are now getting warmed up, your hardware prefetcher is also getting trained. So next time when you would execute the actual program, then it's going to be much more beneficial. Okay, so now we are going to go a bit more detail into how exactly we are going to process the instruction. So as I said, like run ahead mode, processing the instruction is same as the instruction processing, except if it's purely speculative. I cannot emphasize it enough that no architectural, like software visible register memory state is updated in this condition. So it's going to be in a speculative zone. It's like a dreamy zone kind of thing. So once you come out of the run ahead mode, you would just restore the checkpoint. So you would just simply see as if where you have left off. So that's the idea. And of course, L2 misses dependent instructions are identified, because the misses that the processor is actually waiting on, if there is some instruction that you have found inside this run ahead mode that is dependent on that instruction, of course you cannot execute that unless you make some speculation. So that's what it's saying here. At least in the original proposal in 2003 work, the dependent instructions are identified and treated specially, in the sense that they are quickly removed from the instruction, saying that, okay, I cannot execute this instruction. So let's not waste our time here. Let's try to find new instruction that we can execute. If they lead to some memory requests which are supposedly missed, my life is good. That's the benefit here. Yeah, so how exactly it happens? So every instruction that you are going to execute inside the run ahead mode, they have like two types of bit set. So either it can be invalid or it can be valid. Invalid means it's actually dependent on the miss that's happening, right? So you cannot execute them, at least in the original version of the paper. But you have later enhancement that says that you can also predict the value of this load, so that you can still execute some of these invalid instructions that would have been invalidated in the original proposal using this speculated value. So lots of speculation happens inside process. Okay, so invalid values are not used for branch resolution, and so on and so forth. And then what happens when you come out? No, so this is, yeah, so this is saying that, okay, or the oldest instruction is examined for the, so when you come out of the run ahead mode, then what you do is like, and if the instruction itself is an invalid instruction, then you would remove it from the window immediately. But if it is valid instruction, then it would only be removed when you would complete this execution. So that's the thing. And then pseudo-retired instructions, they are free to free their allocated resources. Obviously, when you come out of this, you would free the resource, because now the main execution thread would go in, right? And then there are some other techniques to communicate this dependent loads also, which I'm not going to go too much into detail because they requires much more let's say thought in this thing. And so yeah, so this is how the original proposal implements run-ahead execution in the traditional process. So this is like a Pentium kind of processor design, right? And as you can see, these highlighted ones are only the new additional structures. So run-ahead is typically, let's say, fairly lightweight process in terms of, let's say, overhead that it adds, right? So it just simply adds some sort of run-ahead cache, it adds some checkpointed architecture register files, and then some additions here and there. Okay, so the advantages are that you can essentially generate very accurate prefetch requests for the data or the instructions, because you're essentially executing the program's own code itself. So you have a guarantee that when the program would eventually execute that instruction, it's going to be generating the same value, like same address. It's likely like easier, like relatively simple to implement. Most of the hardware are already built in, as we have shown already here, right? There is no waste of the hardware context, in the sense that you are neither using the simultaneous multi-threading, nor you are using any idle code to do this sort of execution. There is no need to construct a special purpose pre-execution kind of thread that we have seen in the prior works. But there are disadvantages. The disadvantages are we have to execute extra instructions, even though their execution is not making the impact to the checkpoint, because you restored them, you restored their benefits, but then you're anyway executing, so that consumes energy. So you need to make it more efficient, and it limited by branch prediction accuracy. As I said, that it cannot prefetch dependent cache miss, so it cannot execute any instruction that is actually dependent on the original instruction that you are waiting on. So unless that comes back, you cannot execute. So that's, at least the original proposal is not, it's like that. And its effectiveness is limited by the memory level parallelism that I just said. So yeah, so as we mentioned here, that it's actually implemented and evaluated in real life processors, Sunrock, IBM Power 6, NVIDIA Denver, and people have come out so here is some results. I'm not going too much detail, but as you can see that if you have like a traditional prefetcher and add run-ahead on top of it, it actually outperforms. And it outperforms not only, let's say, if you even make your out of order window like 3 times, and if you have like 128 in window with run-ahead, right? So that literally matches the performance of a 3 times more out of order window execution. So that gives you some sort of idea like how powerful run-ahead is. So it's effectively mimicking a 3 times deeper processor without having that complexity. So that's the benefit here. And so yeah, so they have also evaluated in the in order and out of order processor, and then they have said like the benefits are essentially different in different types of architecture. So this is some public information from the Sunrock processor implementation. So they call it Scout. It's like a different name of the run-ahead execution itself. So as you can see, like they have evaluated it for different L2 cache sizes, and for all the cache sizes, it's essentially scouting is better performant than no scouting. And as you can see, like it has that traditional trade-off, right? So if like a same cache space, you have better performance as the same cache budget. Or if you're looking at the same performance design point, then you essentially get the same performance with lower cache space, basically. So that's the idea here. So run-ahead execution, that's the original paper, and I'm going to just quickly go through like lots of works that has been coming up. Essentially, they have evaluated on top of the run-ahead execution. So NVIDIA, so this is an excerpt from the NVIDIA Denver architecture. So they have also used run-ahead execution in their processors, and there are lots of run-ahead enhancements. Like the one that I mentioned, just let's say if your instruction is actually dependent on the load that is missing, then you cannot execute. So they have some enhancement, the address value prediction, so which you can read also. So yeah, so these are the enhancements, and I'm going to quickly go through all of these enhancement works. Like there are lots of works that has been done on this scale. So this is one other work, continuous run ahead, that we are going to discuss in next week's this thing seminar course. If you're interested, then definitely check out that course. Yeah, and this is the other work that I was talking about, decoupled vector run ahead. It's like 20 years after the original proposal, still getting best paper awards on top conference. So that gives you some sort of let's say idea, right? So what Professor Mutlu, and I'm just going to quickly finish this lecture saying that so this is so we have like prior works that kind of like dates back from Professor Mutlu's paper in 2003. So this is dating back from 1997. So as you can see, they have also started looking at the same idea, right? So similar idea, let's say improving data cache performance by pre-executing instruction under a cache miss. So Runahead essentially, like takes this into like the efficiency level that we can think of. And if you look into the future, so microarchitecture essentially, as I cannot emphasize enough, I have said this, I'm just going to conclude here, is that fundamental problems are going to remain fundamental irrespective of the time. Okay, so if you chase always the fundamental problems, like something like, let's say, memory as a critical component, how to reduce the memory latency, how to hide the memory latency, how to, yeah. So these are like fundamental, problems. And so here is the citation for the Test of Time Award. And I mean, I'm not going too much detail. And yeah, so this is something that Professor Mutlu also tells us, and I'm going to tell you, that's my job, so that, follow your passion and chase for the fundamental problems, right? And be resilient. And fundamental problems are going to be fundamental. So they require fundamental rethinking. So if you are interested in this, definitely check out the, more recommending, lots of architecture lectures that covers prefetching as well as run-ahead execution in general, right?
Rahul?
And that would be useful. Yeah. So I would conclude here. I think we are over time a bit more. No, I think we are done. Yeah. So there are some backup slides on this thing, but yeah, mostly we are done. So okay. So if you have any burning question, then I can take it. Otherwise, we can call it a day. Okay. Then let's meet in the next week and have a happy weekend.